Welcome back, and this is the last in the series of videos looking at kinetics. In fact, this is the last video looking at new information for the yellow topics. So once this topic is completed, you will have all the information you need to answer any questions for paper 2. We will in the summer be looking at organic synthesis and practical organics. But those two topics are just bringing together ideas from lower and upper 6th. There's nothing new in them. You're going to need your notes, and we're going to start by considering something we looked at the beginning of the previous topic. What factors affect the rate of a reaction? So we're going to think about the factors that affect the rate of a reaction. If you remember back, we said things like temperature, well, they affected it. We said surface area. We said concentration. And we said a catalyst, and those were the main ones. Now, if we consider our rate equation, if we think about, for example, an SN1 mechanism, we know that the rate is equal to the rate constant K times the concentration of our halogenoalkane. Raised to the power 1. So we've taken into account our concentration term. That one has been taken into account. But we also know that the rate will speed up if we increase the temperature, if we add a catalyst, or if we increase the surface area. So we know that those factors affect the rate of a reaction, but in our rate equation, we only have our concentration term and this K. And this leads us to suspect the fact that K takes into account temperature and surface area and catalyst. So we need to unpack this rate constant K a little more closely. So we're on page 15 of our notes, and we're looking and we're unpacking this rate constant K. So the rate constant K is equal to large A, we call this the Arrhenius constant, times the mathematical quantity E raised to the power minus EA divided by R, which is our gas constant, we've come across that before in gas equations, times the temperature in Kelvin. So here, inside K, so we have the Arrhenius factor, which is affected by surface area. You can think of it as the fraction of particles which collide with the correct orientation. That obviously will increase as the surface area increases. We have the activation energy, which can be altered by the catalyst. So if we reduce the activation energy, therefore K will increase. And we also have the temperature here. And if we increase the temperature, we can say that again, that will increase the rate constant, which will increase K. And for many reactions, it is this rate constant K that determines the overall rate of a reaction. For example, we know there are some reactions, no matter what the concentrations, the rate is very, very fast, almost instantaneous. And the reason for that is this rate constant K value is very large. We also know some reactions where you have to have very high concentrations, and even then it's a very slow reaction. And the reason for that is that K is a very small value. You can also see, because this is an exponential value here, that a small change in temperature or a small change in the activation energy is going to have a large increase on the rate. Because it's exponential, it's going to change K by a large amount. So it's not very useful in that form, but it's much more useful when we can put it into this form. So what we've done here is taken natural logs of both sides. Now, if you don't do maths, you don't need to worry about that, but I would strongly suggest you learn this equation. Ln K is equal to ln A minus EA divided by RT. Okay, we can separate that in further as ln A is minus EA divided by R times 1 over T, and that's important later on. So there's a relationship between the rate constant and the temperature. So ln K is directly proportional to 1 over the temperature. In other words, as temperature increases, K increases, because that's the relationship between them. Our relationship between ln K and EA is similar, but in this case, as EA decreases, K will increase. So you want the lowest possible activation energy at the highest possible temperature to maximize my values of K. So starting with this equation, we have ln K is equal to ln A minus EA divided by R times 1 over the temperature. It might be quite difficult to see, but this is actually the equation of a straight line. So ln K is my Y value, my Y-axis. Ln A is the intercept on that Y-axis. Minus EA over R is my gradient. And 1 over T is my x-axis. So y equals mx plus c. So we can use this idea to find the activation energy for a reaction. What we're going to do is do the same reaction but at different temperatures. We can then plot 1 over the temperature versus the ln of the rate of the reaction, because we're going to keep everything else constant, and we're going to get a straight line. We can measure the gradient of that straight line, and the gradient of the straight line will equal minus EA over R. You should notice that this is a negative gradient, and because it's a negative gradient, EA will always come out as a positive value. Now, there are lots of traps in this one, and you need to be very careful with it. Don't start at 0, because you're just going to waste paper. Here, 1 over the temperature, do remember that temperature needs to be in Kelvin. Ln K is a negative value, so you're going to start off here, say -1, and you're going to go down -2 and so on. So the numbers get bigger as you go down. The gradient, notice it's a negative gradient. Now, because you're dividing by R, which is 8.31 joules per mole per Kelvin, your EA answer initially is going to come out in joules per mole. So you're going to work out your EA value, and its units will be joules per mole. So you should get a very large number at this point. So you need normally to divide it by 1,000 to change it into kilojoules per mole. So just be a little bit careful of that one. But you're going to do several experiments to find the activation energy and to investigate the rate of reaction changes by adding a catalyst. So that finishes these notes looking at kinetics, Kinetics II, and the relationship between kinetics and the mechanism. How we can use kinetics to work out whether or not a reaction is undergoing an SN1 mechanism or an SN2 mechanism. This is very useful for helping to decide which type of mechanism a secondary halogenalkane is undergoing. We've also looked at the Arrhenius equation and its relationship to the activation energy, temperature, and surface area. So you're going to do 2 more experiments looking at activation energies, and there's also loads of questions for you to do at the end of the topic. So until next time, take care, stay safe, bye-bye.